video will cover section 6.6, vectors. So we're going to write the first definition, scalar quantities, which are quantities that involve magnitude but no direction. As Ruben read for us earlier. So a scalar has only a numerical value. And so we're going to be comparing two vectors. And so two vectors are equal. In this case, we will call them V and W, if they have the same magnitude and the same direction. It has to be exactly the same. Now, to find the magnitude and to find the direction, we're going to use two formulas that you guys are very, very used to. And so, for magnitude, and actually it's probably good to mention this, every vector is going to have an initial point. Sometimes that initial point is going to be the origin, which is 0, 0, the coordinate 0, 0, rectangular, okay? And I'll like try to step away from polar a little bit. We're going to revisit them in section 6.5. But I think it's better to cover 6.6 and 6.7 before we do 6.5. So initial point and terminal point. Now, how can you distinguish between them? Well, they'll be denoted by an arrow, okay? So the one that has an arrow, that will be your terminal point. So because of that, we're going to call this vector PQ. And you can use this type of symbol on top. In physics, you see other symbols, right? You might? Okay. Sometimes in engineering classes, they will use different symbols as well. All right, so what we're going to do to calculate the direction is actually, we're going to be using the slope formula. Yeah? So this will be super easy to use. So for direction, we're going to be calculating the slope formula. Sometimes, what kind of symbol do you guys use in geometry? Do you use like a little hat? Okay. All right. So we're going to be using that, and then to denote magnitude, we're going to use this. So it kind of looks like a double absolute value, or like the greatest integer symbol, but it denotes magnitude. So now what we're going to do for magnitude, we're actually going to be using the distance formula. And so that's why it's important to know 2 points, the initial point and the terminal point, because with 2 points you can calculate the direction and you can calculate the distance. Now, right here we have 4 examples, 4 pairs of vectors. And so the first one, you can see clearly that V and W are equal because they have the same magnitude, same direction. It's pretty obvious that they are parallel, so that's how we can tell that they have the same direction. And it's also pretty obvious that they are the same length, so they do have the same magnitude. Now the next one, they have the same magnitude, and maybe it's not so obvious, but if you were to measure them with a ruler, you could see that they do. But you could see that the direction is different, right? So those are not the same. So the only ones that are the same is the first pair. Now, right here, we do have same magnitude. There are equal lengths, same magnitude. However, they might look to you like they have the same slope, but the fact that they go in opposite directions, it makes it have, even though they might have the same slope, it will not work. So what we will do here is, you guys notice how the initial point is here, terminal point is here, and here is the other way. So that's why we say they have opposite directions, so therefore they're not the same. Okay? And then the third step, you can see clearly that one is shorter than the other one, right? So that will be different magnitudes. Although they might have same direction, different magnitudes. Okay, so we're going to compare the two vectors that are next, right here. And we're going to see if they have the same magnitude and direction. So, do you guys want to try it on your own? Because I think this is too easy for you. Yes, Brisa.
Can you use the Pythagorean theorem?
Yeah, so it will be, the Pythagorean theorem will be the same as the distance formula.
Oh.
So remember how the Pythagorean theorem could be like this. And then the distance formula, we don't know what A and B are. However, we get them from the difference of the x coordinates and the difference of the y coordinates. So in reality, you're doing the same thing. Yeah. Okay. So it's right here. How about we do this? You guys on this side, you guys compute the magnitude and the direction of U, and then you guys on this side of V. Okay? And then we'll check. That way will take us less time. So make sure you do use the correct points. And you can see that they're kind of going to the same direction. And instead of calling it D for distance, you could just use the symbol for magnitude, so you get used to it, okay? Yes, Lizzie?
What's the using magnitude?
Both. We're going to have to do both. So magnitude and then direction.
What is the two absolute?
That will be the symbol for magnitude. I know it kind of looks like absolute value or the greatest integer, but that's what we use for magnitude. Sometimes they actually include their arrow on top. Together. Yes, double line, double line. You can have the arrow on top or not, and it will have the same meaning. So if you're doing U or V, make sure you plot your points correctly. If you see that I've made a mistake, please let me know. And so, are you guys getting 45? The square root of 45? So, if you factor that using a perfect square, that will be 9 times 5. Square root of 9 is 3, and then the 5 stays. So, you guys agree that we do have the same magnitude, right? Yeah? Okay. Now let's calculate the slope, and I mean you could use the slope formula. So let me see what's the symbol for direction. The magnitude. Like this one?
I knew how you put a vector sign over.
No, that will be optional, Cassandra. Either or will work, with or without. Okay? Now, if you're taking a class, it will depend on your teacher. It's just good to us. Now for slope, so let's call it the slope of vector u. So that will be, okay, so we need to get the difference of the y, so that will be minus 3 over the difference of the x's, minus 3 minus 0. So that will be minus 6 divided by minus 3, which is positive 2. And the slope of the other vector, so I'm using a subscript just to differentiate which vector I'm talking about. So that would be 0 minus 6 and 0 minus 3. So we get negative 6 over negative 3. And so that gives us positive 6. So because the two, the directions are the exact same thing. Like this?
Yeah, no. Well, it's a line, and instead of having an arrow, you have one side of the arrow.
Could you draw it for me?
But it's confusing for you guys look like this.
It's just one side of the house.
Oh,
Instead of
yeah,
a complete arrow, they just do one side.
Yeah, I've never seen that before.
Really?
I've never seen that. I don't know. So this one is common.
Yeah.
But I don't even know what you guys are talking about with the other symbol. So let's not use that symbol. So let's move on. And so we have two more definitions here to write. So multiplying a vector by any positive real number. Let me find it. Okay.
We don't have that.
Oh, you guys don't have it?
No.
Well, then write it down.
In the back?
Yeah, write it in the back. Yeah, the last page should be blank. Okay, so multiplying a vector by any positive real number, and here we're going to make an exception, except for one, because that will not change anything. It changes the magnitude of the vector but not its direction. Okay, so we can make a vector, and you can see it right here. For example, here is vector b, and if you multiply by a positive number, it could change the magnitude. So in this case, they multiplied by 2. 2 was the scalar quantity. So it made it twice as long, right? The magnitude was multiplied by 2. Now here, you could see if the vector, the original vector here, was multiplied by 1/2. So it shrunk the vector by half, right? Now, when you multiply a vector by a negative number, it's not only it could not only change the magnitude, but it will also change the direction. Okay, so it's gonna go in the opposite direction. So you can see the original is going up, and this one will go down. So the definition we need there is going to be, okay, so multiplying a vector by a negative number reverses the direction of the vector. And it's good to learn a lot of different types of representing vectors. So even if it's a little confusing, it's just better that you make those connections now. Yes.
Is there a way to show that there's a direction going both ways, or is it just going one?
Vectors will only go one way. Yes. So for example, gravity, it's always pulling down. For example, friction. Friction is an interesting one because friction will be like an opposite direction, but it will always act against the work. So if you are thinking about yourself running, so you are using a force vector or a work vector, but then friction is acting in the opposite direction of which you're running. So friction will always be that way, and then gravity will always be that. Yeah, so they can't really have both, unless there's some crazy vector thing that could switch, and I could see that, like maybe in advanced physics or something.
This time of vector?
Time of vector. Time of vector. That's a good question. I wouldn't think so because time, you know what? In fact, time is thought to be a dimension. And if you talk to a mathematician, they will tell you that only 3, maybe 4. But if you talk to a physicist, they could tell you that 20 something dimensions.
Oh, I was like, what do you mean?
Yeah. It's very good. Okay, so scalar multiplication. So anytime you multiply by a constant, you don't need to copy that. I think you will be okay as long as you have these 2 definitions. Okay, and that you know that if the constant is negative, it's going to turn it to the opposite direction, reverse the direction. Okay. Let's take a break in 10 minutes. Is that okay?
Yes.
You're still good? Are you sure? Okay. All right. So we're going to be graphing the vectors here, and what we're going to be doing now is like the basic operations. All right. So we cover scalar multiplication. It makes it longer or shorter or reverse the direction. Now, what we're going to do is add vectors. And I know you don't have it, but you can just make a drawing. Let me see your handout. So it's skipped. Okay. All right. So when you add vectors, just draw right here vector u and vector v. Just draw those 2. Imagine that this one is right here. The dark blue one. So let me make them red. So draw that one, vector u, and then right here, vector v. And so whenever you want to add those 2 vectors, what you do is that you position u and v so that the terminal point of u, which is this one, the terminal point of u right here, coincides with the initial point of v. And right here, the initial point of v will also be this one right here. No, this is just a graphical representation. So you can kind of picture what's happening, but we're going to do it with numbers. We'll do it arithmetically. But the picture helps. So this one sometimes is called the parallelogram rule. And so let me see if I can do this. Oh, they are together. I was going to separate them. Let me see if I can. So let's say you have your 2 vectors. You have your 2 vectors like that, right? And this is vector u, this is vector v. So what this is telling me is that you want to position the terminal point of this one so that it coincides or overlaps with the initial point of the other. Like that. All right? And so what you do is the resultant vector, the actual addition, which you can see here in dark blue, is longer, right? It's not just longer, but it's actually the vector that runs from here all the way to here. right? They call it parallelogram rule. I'll show you another example why they call it that. All right, so that's what happens graphically. Now let's do it with numbers. That will be your example 2, and then I think we can take a break. Yes, Azim.
But it says u plus v. But isn't u plus v actually one of the vector? That's created by.
Well, you're not actually putting them one next to the other. Like if we were, I wish I could rotate it. Like that. Is that what you were thinking? Let's see.
Why is it saying that it's u plus v is actually short?
Because we're not really adding them like that together. We're actually adding, let me see, when we do it mathematically,
It's not going to take that direction.
you guys don't have that slide either, huh?
No.
Okay, so I'm going to have to print those for you. But you guys have that.
Yes.
Okay, so we do have this. Now we're going to see what happens when you subtract 2 vectors like we are seeing here. And keep in mind that when you subtract a vector, when you multiply a vector by a scalar multiple, and let's just call it -1. So what that will do is make this vector be negative. And so if a vector is negative, then it's going to change the direction to its opposite direction. So I'm going to start, I'm going to use this red marker so you can kind of follow it. And so here's vector u. And so what's happening, and of course, here's the other one, vector v. Okay, cool. So here's vector u, all right, the run and red. And so since we are subtracting it, it's going to be with the direction reverse. Like that. So now it's there, right? So then we use the same rule that we used before, that where we talk about putting the terminal point of the first vector, which is here in red, plus the other vector, which is here in green, and then the resultant vector was the one that went from the initial point to the terminal point, okay? So now when we go to the subtraction, not only I have to reverse the direction, but then if I position them that way, and here's where you can kind of see the parallelogram, okay? So remember the rule. The rule was, maybe I should write it.
Wait, where's the negative?
Why did you multiply by -1? Oh, because we are subtracting. Oh, so we're talking now about difference. So it was v minus u. So that's why I multiplied. Oh, right. Okay. U by -1 because we are gonna. It's like we're adding a negative vector. Okay. Okay.
Also, v stays positive, that's why it's negative.
Correct. V stays positive. The only one that goes to negative is u. Correct. Yes. So let me copy this definition for you. Okay, so the difference of 2 vectors, it is defined as this. So v minus u is equal to v plus -u. So that's what I was saying about adding a negative vector. Where -u is a scalar multiplication of u times -1. So that's what I was showing on the right side of the board. Maybe I should have wrote that before. So that gives us -u, right? So that's why we reverse the direction. Okay, so now let's follow the rule that said, okay, you're going to position the first vector first vector, which is vector B, okay? The marker. Just write it again. So if you notice, the one that we did before, we were actually doing u plus b, right? So that is why we took the terminal point of u, which is this one. But now we're doing b minus u, okay? So we're going to take the terminal point of vector b, right? I just don't want you guys to be confused. So the terminal point of b will be this one right here. This point right here. So we're going to take that one. And then we're going to overlap it with that one. And I think this is okay, so let's retrace our steps. The terminal point of vector b coincides with the initial point of vector negative u. Yes, so we're good. We're good. So then from there, the actual vector that we get will be this one here. Okay, now I know some of you are not very visual, but once we do it with numbers, it might make a little more sense to you. So this is what I was referring as the parallelogram rule earlier. It does look like a parallelogram, right? So I believe that the parallelogram comes from here. The vector used to be here, you position it here, and then you have that one reversed. Okay, if you don't understand that geometric representation, hopefully the one with numbers will help you with that. Now, what we're going to do is not consider any initial point to be anywhere, but only at the origin, okay? And so we're going to refer to those vectors as the I and j vectors. Sometimes I refer to them as the I component and the j component. And so that you know what I'm talking about, the I component is going to give you the horizontal distance of it, this A right here. And the B component is going to give you the vertical distance right there. So now we're saying that our initial point is always going to be at the origin, and when it's not, we're actually going to learn how to convert it to that. So then if you consider the horizontal component, which is the I component, and the vertical component, which is the B component, that's what will give you the terminal point of your vector. Okay, so this is terminal, is given by those coordinates, by the I and j component, and then the origin, the initial point will be at the origin. Okay, and this is the vector, the actual vector. Okay, so now we're going to start looking at them that way. And of course, here what it says is that vector I and vector j, bless you, are the unit vectors. That means that they measure one unit. We don't know if it's inches, kilometers, whatever. And so vector I is 1 unit on the x-axis, and vector j is 1 unit on the y-axis. All right, so that's why we can translate them into x, y coordinates or vertical and horizontal distance. All right, so a vector that is written that way in the form ij, everything that I already told you, horizontal and vertical. And for the magnitude, that's when we will be using the Pythagorean Theorem. So someone asked me that earlier. Who was that? Brisa. Very good. So maybe you were thinking about that one right there. And yes, with that one, we don't even need to worry about the distance formula because the initial point is at the origin. So it's like we were doing something like, if we were to use the distance formula, it would look like this. And so you do that, and a minus 0 is just a, b minus 0 is just b. Yeah? So when your initial point is at the origin, you don't have to worry about distance formula and just jump straight to the Pythagorean theorem for magnitude.
Just when it's in the origin, right?
Yes, it has to be at the origin. All right, so let's go ahead and find the magnitude here for this one. And so what this is telling me is that the scalar multiple of the I component is -3. So we're going to go -3 units right here. And then the vertical component is +4. So it's like we're multiplying the unit vector j times 4. So then it goes up to here. Okay? But if we wanted to add them, the addition will be you position this one here, and the resultant vector will be right here. Okay? So this one will be vector b, which is represented by -3i plus 4j. In other words, the initial point is at 0, 0, and the terminal point is at -3, 4. Now, to find the magnitude numerically, we could use the Pythagorean theorem. So if a is -3, we square it, and then b is 4, and we square it. So this is 9 plus 16, which is the square root of 25, which is going to be +5. Now, would you guys say it's positive or -5? I don't know, to be honest. I would say positive because it's going up, but I'm going to check on the book just to make sure. It will be positive, yes. You're all right. That is true. So the magnitude at all is always going to be positive. Thank you, Annette. Thank you for that. So the direction is the only one that could be both, right? Magnitude always positive. Thank you. All right, so let's try for you guys to do checkpoint 2. You know what? Let's just skip it because I don't want to be cramming.
Wait, I have a question.
Yes.
You know how you did the green one before it was on the y-axis?
Yes.
Why did you move it?
Oh, I just moved it to kind of follow the same rule that I was doing before. That how you put it, like if you were to add them, you don't really need to do that. You don't need
So
to
you
do
could
that.
just do it.
You could just do it this way to find the magnitude. Yeah.
Oh, okay.
In fact, you could just plot it. I mean, I was just doing that to demonstrate how that was the vector j, but when you add vector I, the blue one, plus vector j, you position the initial point of vector j at the terminal point of vector
Okay.
I. But you don't need to do so. That was just for shows. You could just know that the initial point is at the origin and the terminal point is this. And that's how you can plot it easier.
Okay.
Okay, you don't need to really draw the blue vector or the green vector here. All right, so let's just do this one just to make sure that we're all on the same page. So sketch the vector. So you could start by the initial point at the origin. And then what do you guys think the terminal point will be? So we'll be at the coordinates. Remember, this 3 gives you the x coordinate, positive 3. And then this negative 3 is going to give you the y coordinate. So that's where it will be. So from 0, 0 to 3, comma, negative 3. Okay, and find its magnitude. So we could just jump in straight to the Pythagorean Theorem. So will be the square root of 18, or we could factor 18 as 9 times 2, because 9 is a perfect square. Square root of 9 is 3, and the square root of 2 stays inside. Now, if we were asked to find the direction, what would you guys say the direction is? So if we go from the initial to the terminal, and we calculate the slope here, you could see it will go 3 units down, 1, 2, 3, and then 3 to the right. So the slope, which represents the direction, will be negative 3 over 3, okay? And that will be going down. All right. But if we were the opposite, if this was our initial and this was our terminal, then the direction would be also the opposite sign. Okay? So it depends. Where's your initial? Where's your terminal? Is it too hot in here? Yes? Okay. Now in this case, the origin might not be at the, the initial point might not be at the origin. So we're going to make them be at the origin because those type of vectors are easier to work with. And so if you notice here, the example is giving us initial point, the coordinates 3, negative 1. And then the terminal point is happening here at negative 2, 5. And so what we want to do, and here's a very good example of a vector that is not at the origin, but here is how they were able to make that happen, okay? The vector has the same magnitude and the same direction. It was just the initial point was shifted. And so the way we're going to achieve that is by right here. Because here the difference of the axis is giving us the scalar for the horizontal component. And this difference right here of the y's is giving us the scalar of the vertical component. So remember how B-class, can we just use distance formula, right? Pythagorean Theorem. And so, yeah, you could use that if you are given your vector in terms of like that, where that represents A and that represents B. But when you are not given that, then you use the variation of Pythagorean Theorem, which is like x2 minus x1 squared plus y2 minus y1 squared. And so that right here, this A is being represented by that, which will be the same thing. Okay? Do we all agree? Yes? All right. So let's go ahead and put that into practice. So we're going to make that vector have the initial point at the origin. So let's just plot it first. So it was at 3, negative 1, the initial, and the terminal was at negative 2, 5. So now we want to write it in terms of I and j. So what we're going to do is take the difference of the x values. So let's say -2 minus 3 times I plus, and then take the difference of the y value. So that will be 5 minus -1, and that will be the j component. So here we will get -5 times I. Here we'll get 5 plus 1 times j. So the vector is actually -5i plus 6j. And so I'm going to plot that vector, but now considering my initial point is at the origin, and then my terminal point is actually going to be at the point -5, 6. And how do I know that? Because those numbers are coming from here. So -5, 6. Initial there. Right? And so that's how it will look. And if I was to overlap them, you can see that they are the same magnitude. Okay? And they are the same direction as well. I mean, they're not perfectly straight. Okay. Okay. Do you guys have any questions so far? So this is going to be called representing a vector in rectangular coordinates, right? And when it says write it in terms of I and j, that means that the initial side must be at the origin. Okay, don't forget that. Okay, now you could add and you could subtract vectors if they are in those terms, in I and j terms. And just like if you were to add or subtract imaginary numbers, do you guys remember how to do that? Imaginary numbers, so let's say complex numbers that have a real and an imaginary part. What do you do when you add them? Do you add the real part with the imaginary part? No. Okay, you add the real with the real. And let me give you an example. So if you have 2 plus 3i, and then I tell you add 5 plus 6i. So that will be you add the real with the real, and then the imaginary with the imaginary, right? Very simple. So when we're adding vectors, we're going to do something similar if they are in I and j terms. So you're going to be adding the I with the i's and the j's with the j's. Okay? Very simple. The way I have it explained here is that if you are adding, then you add the horizontal components and you add the vertical components. And if you are subtracting, then you subtract the horizontal components, you subtract the vertical components. All right? I don't really have an issue, like however you want to write it. Personally, I like to just do it like if I was combining like terms. Are you guys okay with that? Let me show you. So let's say I want to add these two vectors, right? So vector B is 5i plus 4j. And then vector W is 6i minus 9j. So if I combine like terms, 5i plus 6i will be 11i. And 4j minus 9j will be negative 5j. And that's it. That's it. And if we were to plot them both, I mean, not both, but all three of them, vector B, vector W, and the addition, you could see the same thing that I was explaining with moving the vectors. Now let's do part B. Part B says vector B minus W. Now here you need to be careful because of this minus right here, okay? So vector B is 5i plus 4j, and we're going to subtract vector w, so I'm going to put it in parentheses. So 6I minus 9j. And of course, I need to make sure to distribute that parentheses because we're subtracting the whole vector. So in this case, we will have 5I plus 4j minus 6I, and then what is negative times negative? Positive, so 9j. So now let's combine my terms. We have 5I minus 6I, so that is negative I. And here for j, we have 4j plus 9j, that will be 13j. Okay. So that's adding and subtracting in terms of I and j. Let's move on. Okay, now we could have also scalar multiplication with a vector that is written in terms of I and j, like that. And so what we do here is we literally just distribute that scalar to the I component and to the j component. And that's what we're going to do. Okay? So remember, when you multiply a vector by a scalar, in this case, will that make the vector longer, shorter? What will happen? 6 times the vector. What? Longer? Yes? So that will increase the direction or the magnitude? Okay, the magnitude. So, vector 6 times 3 will be 6 times 5I plus 4j. And so if I was to do it like it says right here, it will look like this. 6 times 5, and then 6 times 4. And so we will get 30 times I plus 24 times j. Now, if you just want to distribute it from here, you will get the same result. So 6 times 5I is 30I, and then 6 times 4j is 24j. Right? So you do get the same result, so that is up to you which way you want to do it, as long as you get to it quickly, before you forget. And I've been told before that I make math look easy, and you might feel that way when you're in the class, but then as soon as you leave, you forget. And so that's why you need to stay on top of your homework. Okay, any question about that one? Oh, we still have the part B. So now part B, we have -3 times the vector. And so that one, it is going to make it longer, but it's also going to change the what? Direction. Very good. So let's just do it the short way in this case. So vector B is 5I plus 4j, and so that will be -15I minus 12j. Okay, next one, we're going to include both. We're going to include scalar multiplication because we're multiplying vector B times 4. And we're also going to subtract, okay? And we're also multiplying 2 times w. So if you guys can do that, just kind of practice how to do that, please. So 4 times this vector. Which one? You know what, we could do that. We could multiply by -2, but then once we put them together, let's not use negative again. So we will use positive. So that's up to you. You could multiply by -2 here, and then when you put them together, whatever you get from here, you will just add it to the other one. I'll show you. So if we multiply this by 4, we get that, right? Now, if we multiply -2 times 6I minus 9j, that will be -12I plus 18j. So since we already account for that negative right here, then all we need to do is add this, right? And mean, if you want to do it vertically, that's fine with me. So it will be 20 minus 12. That will be 8i. 16 plus 18, that will be 34. Now, the other way that I was going to do it, Sandra, was you get 4b, right? And so we got that it was 20i plus 16j. Now, I was going to multiply 2 times w, so that would have been 12i minus 18j. And then I was going to do this. 4b minus 2w is equal to 20i plus 16j, and then minus that one. So then this was going to be negative, and this is going to be positive. So 20 minus 12, and then 16 minus plus, thank you, 34. So I will probably say that your method is better. So we just distribute the -2 there. It will save us some steps. But again, you guys are free to do whichever method you want, as long as you get it right. Okay? Just be very careful because you guys are pretty bad about distributing negatives. Right? So be careful on the test. All right, so next page. Any other questions yet for the slide? All right, now the zero vector. And so just like all real numbers have 0, vectors also have something called, actually matrices also have the 0 matrix. So in this case, we also have a thing called the 0 vector. And so the 0 vector, the has a magnitude equal to 0, and also it has no direction. And we could still express it in terms of I and j, and it would just look like that. Okay, now here's a summary of all the properties that we have with vectors. We have covered most of them, I think. Thank you. So right here we have vectors u, v, and w. And so we have the addition is commutative, meaning that you could subtract u plus v is the same as v plus u. If you reverse them, you get the same, as long as you're adding them. Associative property, that means that you could add 2 at a time and then the third one. Or you could add the last 2 and then the first one, and you will get the same. But you can associate them in different ways, and if you add, you're still getting the same. Now, the additive identity. So do you guys remember how I always bother you with what's the identity? What's the identity? So what's the identity of real numbers? Do you guys remember? The additive one. What can you add to a number and still get the same number? 0. So 0, the number 0 is the additive identity of real numbers. But also, the 0 vector is the additive identity of vectors. Meaning that if you add any vector to the 0 vector, you get the same vector. Now, just like we have additive identity, we're going to have additive, multiplicative identity. Okay? And what is that identity of numbers? What number can you multiply 3 so that you get 3? 1. So just like the real numbers have that multiplicative identity, remember we're using that with matrices? Vectors also have that, and that will be scalar 1, right? All right, so identities, inverses, same thing as with numbers. If you have number 4, what do you need to add to number 4 to get the identity, which happens to be 0? -4. So same thing with vectors. If you have a vector and you want to get the 0 vector, then you add the opposite of that vector. All right? We have here associative for scalar multiplication. Same thing. Associative for multiplying, and you distribute like this, you will get the same. That will be exactly the same. Or if you're adding 2 scalars, you can add them first and then multiply them, or you can multiply them one at a time, and they will give you the same thing. We went over that, and magnitude. Of course, you already know that when you multiply a number times a vector, it will increase or decrease the magnitude, right? So that's what we're showing here, the magnitude property. All right. Okay. So the unit vector, this one is a vector which magnitude is equal to 1. All right. So let me see what I need you to copy there. So the unit vector is defined to be a vector whose magnitude is 1. Okay, and we're going to need to know how to find this unit vector when we get to the next section, which is 6.7. So the rule here is that you're going to take the original vector and you're going to divide by the magnitude of the original vector. So let's say that you have a vector that is 3 units long. So if you, I already told you, right? The magnitude is 3. So if you take the vector and then you divide by 3, you will just be getting the chunk of that vector. So that will be the unit vector. All right? So let's see how we're going to do that. So first of all, we need to find the magnitude of the vector. Here's the vector in question. And so the magnitude, since it is in I and j, we could just use Pythagorean Theorem. So that will be 5 squared plus negative 12 squared. And that's going to give us 25 plus 144, which will be the square root of 169, which is 13. Now, what we're going to do is take the vector and divide by its magnitude. And so it will look like this. 5i minus 12j divided by the magnitude, which we found to be 13. Now, we're not just going to leave it like that, because we want to separate it in terms of I and j. So we're going to split the fraction. So this will be 5 over 13i minus 12 over 13j. And so this will be the answer, the unit vector of vector B. Any question on that one? Okay, so next one. So direction angle. Okay. So let's see. The components A and B can be expressed. Don't be copying, please. In terms of the magnitude of the vector, which we're going to call B, and the angle theta that B makes with the positive x-axis. So just like angles that we consider to be in standard position, so you start with the positive x-axis, and then the other side of the direction angle, this is what will be direction angle. will come from that positive x-axis to, and the terminal side of the angle will be the vector itself. All right, so we'll stop here. Hold on a second, because the next two problems are gonna take us probably at least 5 minutes each. So that's why, okay? We'll finish 6.7 and then Friday, hopefully, we can do that. Yes?
The files will get saved.
Oh, the file, great.
So we bring it next week?
What do you get on Wednesday? It's okay, because that grade is not only in your progress report. Bye. Bye, guys.